In this lecture video, we're going to see how we can use the properties of the standard normal distribution for normal distributions that are not standard. With a standard normal distribution, we have a mean of 0 and a standard deviation of 1, which means that each data value is the same as that data value's z-score. With a non-standard normal distribution, we don't require that the mean is 0. The mean can be anything. We also don't require that the standard deviation be 1. The standard deviation can also be anything. So we don't have the same property. Each data value is not the same as its corresponding z-score. But thankfully, there's a very simple way to translate a non-standard normal distribution to the scale of a standard normal distribution. We simply switch to z-scores. By using the property that z is equal to x minus mu divided by sigma, or x minus the mean divided by the standard deviation, we can translate the scale of a non-standard normal distribution to a standard normal distribution. The z-score corresponding to the mean is 0, and each data value will have its own corresponding z-score. By switching to z-scores, we can use all of the properties of the standard normal distribution. Let's take a look at an example. Suppose that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. We'll start by finding the probability that a randomly selected adult has an IQ score less than 115. Let's start by drawing a picture of a normal distribution. We have a mean of 100 and a standard deviation of 15. Wanting to know the probability of a randomly selected adult having an IQ score of less than 115 is equivalent to finding the area under the curve to the left of 115. We'll start by translating our data values, which are the IQ scores, to the corresponding z-scores. With z-scores, the mean is equal to 0 and the standard deviation is equal to 1. And we can find the corresponding z-score for 115. We can find z by finding x minus the mean divided by the standard deviation. In this case, we have 115 for our x value, 100 for the mean, and 15 for the standard deviation. So we find that 115 has a z-score of 1. Finding the area to the left of an IQ score of 115 is now the equivalent of finding the area to the left of a z-score of 1. For this example, let's take a quick look at our z-table. We are interested in a z-score of positive 1, and looking at the positive z-score table, we find that the left area corresponding to a z-score of 1.00 is 0.8413. To summarize what we just did, we found the area to the left of z equals 1. That's the same thing as the probability of an IQ score being less than 115. And we found this area to be 0.8413, or the probability of a randomly selected adult having an IQ score less than 115 is about 84.13%. Now, in order for a person to qualify for Mensa, they have to have an IQ score that's at least 131.5. Let's find the probability that a randomly selected adult would qualify. That is, we want to find the probability of an IQ score being greater than 131.5. Let's change this on our picture. We are now interested in an IQ score of 131.5, which translates to a z-score of 131.5 minus 100 divided by 15, or 2.10. That is, 131.5 corresponds to a value of 2.10 on our z-scale. Wanting to find the probability that an IQ score is greater than 131.5 is equivalent to finding the area under the curve to the right of 131.5, which we now know is the equivalent to finding the area under the curve to the right of a z-score of 2.1. Let's look at our z-table. On our positive z-table, we are now interested in a z-score of 2.10, which has a corresponding left area of 0.9821. That is, this area to the left is 0.9821, but that's not the area we're looking for. We want the area to the right. The probability of having an IQ score greater than 131.5 is equal to 1 minus the probability of having an IQ score less than 131.5, which is what we just found with this corresponding area. So our probability is equal to 1 minus 0.9821, or 0.0179. This area to the right is 0.0179. Now we know that the probability of a randomly selected adult qualifying for Mensa is about 1.79%, or 0.0179. Let's take a look at a different example. In this example, we are told that the liquid in regular-sized Diet 7-Up cans are normally distributed with a mean of 12 fluid ounces and a standard deviation of 1.5 fluid ounces. We're going to find the probability that a given can will be between 11.5 and 12.5 fluid ounces. As always, let's start with our picture of a normal distribution. In this case, we have a mean of 12 and a standard deviation of 1.5. We want to find the probability of a can being between 11.5 and 12.5. That is, we're looking for the area under the curve between 11.5 and 12.5. We'll start by translating our X values, which in this case are in ounces, to their corresponding Z-scores. The Z-score corresponding to the mean is of course 0, and here the standard deviation is equal to 1. The Z-score for 12.5 is equal to 12.5 minus 12 divided by 1.5, or 0.33. The Z-score corresponding to 11.5 is 11.5 minus 12 divided by 1.5, or negative 0.33. Let's add those to our picture. Now we know that the area under the curve between 11.5 and 12.5 ounces is equivalent to the area under the curve between Z-scores of negative 0.33 and positive 0.33. Take a look at your Z-table and notice that the area to the left of negative 0.33, that's this area here, is equal to 0.3707. And the area to the left of positive 0.33, that's everything to the left of here, is equal to 0.6293. So the area between the Z-scores negative 0.33 and positive 0.33 is the difference between these two values. That is, the probability of a can having a volume between 11.5 and 12.5 is equal to the probability of the volume being less than 12.5 minus the probability of the volume being less than 11.5. We found that the probability of the volume being less than 12.5 is 0.6293, and the probability of the volume being less than 11.5 is 0.3707. The probability that we want, or the area under the curve between these two data values, is 0.2586. So, the probability of the volume of a randomly selected can being between 11.5 and 12.5 fluid ounces is about 25.86%, 0.2586. In this next example, we are told that a local builder wants to design a playhouse to be used exclusively by the pre-kindergarten classes at a local school. The students in these classes are 4 years old, and the height of an average 4-year-old is 40 inches, with a standard deviation of 4 inches. The builder wants to make a door on the playhouse such that 97% of the children can fit through it without ducking. How tall should he make this door? Let's start with our picture. We have a mean height of 40 inches and a standard deviation of 4 inches. Our data values on this scale are given in inches. The concept here is that we can never please everyone, but we can have a threshold, and in this case, that's 97%. This builder will be happy if at least 97% of children can walk through this door without ducking. The question is, where is that line? What is this value for X so that 97% of 4-year-olds have heights underneath it? We want a left area of 0.97 or 0.9700. Let's take a look at our Z-table. This time we want to look in the body of the Z-table and look for an area that's as close to 0.97 as possible. Scanning the table, the closest thing we find is 0.9699, which corresponds to a Z-score of 1.88. Let's take this information back to our example. We found that this left area corresponds to a Z value of 1.88. That's not our X value. Z-scores are calculated by finding X minus mu divided by sigma. This time, we need to find X. We already have Z. Solving this equation for X instead, we have Z sigma equals X minus mu, or Z sigma plus mu equals x. Or flipping this around, we have x is equal to z sigma plus mu. Substituting the value of 1.88 for z, we find that x is equal to 1.88 times sigma, or 4, plus mu, or 40. Simplifying, we find that the data value we are looking for, the height in inches, is 47.52 inches. That is, 97% of 4-year-old children will fit under a door that is 47.52 inches. Different situations warrant different definitions of significantly high and significantly low. A typical value that we use is 5%. That is, the highest 5% is considered significantly high, and the lowest 5% is considered significantly low. So for a given data set, the value of x is significantly high if the probability of x or greater is less than or equal to 0.05. And a data value x is significantly low if the probability of x or less is less than or equal to 0.05. Let's use this definition for our next example. We're going to use that preceding criteria to identify pulse rates of women that are significantly low or significantly high. We're told that women have normally distributed pulse rates with a mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. Let's draw this picture. We have a mean of 74 and a standard deviation of 12.5. We want to find the thresholds so that 5% is left in the left tail and 5% is left in the right tail. Our x values here are beats per minute. And translating this to z-scores, notice that this z-score will have a left area of 0.05, and this z-score will have a left area of 0.95. Take a look at your z-table. In the negative z-score table, can you find an area that's 0.05? The z-score with a left area of 0.05 is negative 1.645, and the positive z-score that has a left area of 0.95 is positive 1.645. Translating these scores to x values, or beats per minute, will give us our thresholds for significantly low and significantly high. Starting with our z-score to the left, we find the corresponding x value by finding z times sigma plus mu. In this case, that's negative 1.645 times 12.5 plus 74. We have an x value of 53.4 beats per minute. And now for the value to the right, we find that x is equal to positive 1.645 times 12.5 plus 74, or x is equal to 94.6 beats per minute. So what does this mean? This means that for women, a significantly low pulse rate is anything 53.4 beats per minute or less, and significantly high is anything 94.6 beats per minute or more. That concludes this lecture video on applications of the normal distribution.